When you're working with probability and counting, oftentimes you want to figure out how many ways you can draw a set of objects from a larger set where the order doesn't matter. The order of the draw does not matter. This happens in situations like in poker, where you might draw a 5-card hand from the deck of 52, and what you have in your hand, the value of your hand does not depend on which card came first, second, third, fourth, or fifth in the draw. Only what counts is what cards you have in your hand after all the drawing has been done. And in this situation, you're working with combinations rather than permutations, because in this situation, order does not matter. So the number of ways you can choose 3 objects from a set of n, we call that n choose r. It's written these 3 ways: n c r like that, c n r like that, or n choose r like that. Now when people see that, they get confused and they think that that's supposed to be a fraction or a division or a ratio, and there should be a fraction bar in there. But there is no fraction bar in there. It's not a fraction. It is a choose. Repeat that to yourself as many times as necessary. Whenever you see this expression, always say n choose r, n choose r, n choose r, until it's ingrained in your brain. There is no fraction bar. It's not a division. It's not a ratio. Okay? It's a choose. Now, how do you find this n choose r? Well, if you think about the number of permutations of n objects taken r at a time, and then you divide by the number of ways you could permute those r object, which is r factorial, you can get the formula for n choose r. Okay? Order doesn't matter, so we're going to divide out all of those redundant orderings. And what you get is n choose r, however you write it, this way, or this way, is equal to npr divided by r factorial. Now npr is n factorial over n minus r factorial, and so we just have this extra r factorial in the denominator here that we didn't have when we were calculating permutations. Now we can apply this formula. If you take 5 choose 2, it's 5 factorial over 5 minus 2 factorial times 2 factorial. 5 factorial in the numerator. 5 minus 2 factorial is 3 factorial. So you have 3 factorial and 2 factorial in the denominator. And you can evaluate all those things. 5 factorial is 120, 3 factorial is 6, 2 factorial is 2. So you have 100 over 6 times 2, which is 120 over 6 times 2. 120 over 12 is 10. Now if you do 5 choose 3, you'll have 5 factorial over 5 minus 3 factorial times 3 factorial. But 5 minus 3 factorial is 2 factorial. And you'll see that this denominator matches that one. It's just the order of the factorials reversed. But that makes no difference when you're multiplying what order they come in. So this works out to be the same as that. And there's a reason for that. If you have 5 objects and you choose 2 to take out of the set, you're implicitly choosing 3 to leave behind in the set. And so the number of ways you can choose 2 to take out is equal to the number of ways you can choose 3 to leave in. So these have to be equal. And that's a general truth whenever you're doing chooses. If you choose r object out of a set of n, that's the same as choosing n minus r objects out of the set of n. So these are always going to be equal. You can make other general statements about chooses. N choose n, where you're choosing everything, can only happen one way. You're taking them all. N choose 0 can only happen one way. You're not taking any. So you're leaving them all behind. And then n choose 1 is equal to n. You could take the first or the second or the third or the fourth, etc. objects. There are n available that you could take one of. And so n choose 1 is going to be n. And then n choose n minus 1 is also 1. You're basically choosing 1 to leave behind. You're taking everything but 1. So you're leaving 1 behind. And you can prove those with the formula for the chooses, or you could just trust your intuition on that. It's I think it makes intuitive sense. And if it doesn't, you can prove them to yourself using the formula. Remember, 0 factorial is 1. Okay, that's a convention about factorials that you might need if you're trying to prove these relationships. Now you can try a few on your own. We have we have 3 chooses here: 6 choose 2, 7 choose 5, and 8 choose 5. And you can pause the video and you can find those using the formula, and then we'll come back in a minute and see how you did. Okay, welcome back. 6 choose 2, plug 6 and 2 into the formula. Simplify it down, you get 720 over 48, which is 15. 7 choose 5, you plug 7 and 5 into the formula. You get 5,040 over 240, which is 21. And then 8 choose 5, plug 8 and 5 into the formula for n and r. Simplify, you get 40,320 over 720, which is 56. Now you can find these chooses on your calculator. Okay, it's pretty simple to do. You type the value of n, then you go to MathPRB3 and select NCR, and then type the value of r and enter. So if you want to do these up here, the first thing you do is type the top number in your choose, which in this case is 6, and then you go to MathPRB and then select number 3 off the list right there, and then type the bottom number, which in this case is 2, and you get 15. 7 choose 5 is 21, and 8 choose 5 is 56, as we got with the formula. And you can see that working with the calculator is much, much faster. And oftentimes, you're not going to want to use this formula and try to calculate these combinations by hand, because the numbers are going to be big and the factorials get to be really, really big and very difficult to work with. But the calculator can handle a lot of these, and it's often much faster to let the calculator do that. So again, anytime you want to find a combination on TI-84, type the value of n and then go to MathPRB3, which is NCR, and then type the value of r and enter, and you'll be all set. Now you can pause your video again and evaluate these 3 chooses on your calculator, and it probably won't take you but a minute. And pause your video and come back and check your work. Okay, welcome back. 10 choose 4 is 210. 12 choose 9 is 220. And 9 choose 4 is 126. I hope those worked out for you. If they didn't, go back and check your typing. And we're going to use combinations a lot when we're working with the binomial distributions. And that's primarily why you need those in an AP statistics course. We generally don't do a lot of counting otherwise than when we're talking about those specific distributions like the binomial. So we'll look at that in much more detail in the coming weeks.